欢迎各位来到科技大师讲座的校庆特别场的现场。我是今天的司仪，来自大学艺术团的黄诗佳。
Welcome to the lectures of Master Series of Science and Technology. I'm the host today, Yuan Zhangyue from the MUST Art Group.
今天我们非常荣幸地邀请到大卫·朱维特教授，为我们带来《太阳系外之来客》的校庆特别场科技大师讲座。他是美国国家科学院院士、美国艺术与科学学院院士，著名天文学家。
Today, we are very honored to invite Professor David JEWITT, member of the United States National Academy of Sciences, renowned astronomer, to bring us a lecture on visitors from beyond the solar system.
让我们以热烈的掌声欢迎大卫·朱维特教授的到来。
Let's give a big round of applause to Professor David JEWITT.
在活动开始前，我们将拍摄一张全场大合照，有请摄影师移步至台上。
Now we would like to invite you all to take a group photo.
请大家望向镜头，合影留念。
Please look at the camera and be ready.
请准备。
3, 2, 1. 我们再拍摄一张大合照。Please look at the camera and be ready. Thank you all. 感谢各位。
现在，让我们有请澳门科技大学副校监校长李行伟讲座教授移步至台上，为本次的讲座致辞。
May we have the honor to invite Chair Professor Joseph Hangwei Lee, Vice Chancellor and President of Macau University of Science and Technology, to deliver a speech.
Distinguished guests, colleagues, teachers, and students, ladies and gentlemen, good morning. We are very honored to have with us Professor David JEWITT, a world-renowned astronomer, as the keynote speaker for today's special Great Masters of Science and Technology lecture. Professor JEWITT has just received the MUST Honorary Doctor of Science degree just an hour ago. So first of all, on behalf of the university, I'd like to warmly welcome Professor JEWITT. And I would like to invite all students in the audience to join me in congratulating Dr. JEWITT for this highest honor of the university. Congratulations, Professor JEWITT. Professor David JEWITT is a professor of astronomy in the University of California at Los Angeles, UCLA, and the director of UCLA's Institute for Planets and Exoplanets. He's an eminent planetary scientist, best known for his discovery of the first Kuiper belt object and resolving many questions relating to the evolution of the solar system. He has published over 200 science papers in the most prestigious journals. He is a member of the US National Academy of Sciences and a foreign member of the Norwegian Academy of Science and Letters. He is also a recipient of the prestigious Shaw Prize and the prestigious Kavli Prize for his contributions to astronomy. Professor JEWITT's passion on astronomy can be seen from his discovery of over 40 minor planets or asteroids. He is well known for his flair and achievements in public outreach. He is one of the few who can explain and communicate astronomy and astrophysics effectively to the public through BBC interviews and articles in Scientific American, etc. And his dedication and commitment have touched generations of students to pursue studies of the universe. He has also helped train some of our younger colleagues, some of our younger scientists in our Space Science Institute in the past. So MUST is extremely honored to have established a deeper connection with Professor JEWITT today, and we look forward to further collaboration exchanges with him. The title of Professor JEWITT's lecture today is Visitors from Beyond the Solar System. We look forward to his wonderful sharing. Thank you.
感谢李校长的致辞，请留步。
Thank you, President Lee. Please remain on the stage for a souvenir presentation ceremony.
下面将进行纪念品致送仪式，有请大卫·朱维特教授移步至台上。
May we have the honor to invite Professor David JEWITT to come to the stage for a souvenir presentation ceremony. May we invite President Lee to present the souvenir to Professor David JEWITT.
有请李校长向大卫·朱维特教授致送纪念品。
Please look at the camera and be ready.
请二位望向镜头，合影留念。
Thank you, President Lee and Professor David JEWITT. Professor David JEWITT, please remain on the stage, and President Lee, please be seated.
谢谢二位，大卫·朱维特教授请留步，李校长请移步至台下就座。讲座现在正式开始，让我们掌声欢迎大卫·朱维特教授为我们带来《太阳系外之来客》的讲座。
Now the lecture begins. Let's welcome Professor David JEWITT.
Okay, thank you very much. I think there should be a translation. Ah, there you go. There should be a translation at the bottom of the screen, which I hope is a good translation. But I will never know because I don't read Chinese. So today I wanted to talk about something quite new in astronomy. So not Kuiper Belt, not comets, but a new kind of body in the solar system. But to do that, I need to give a lot of background because my assumption is that this is not your subject. This is not your main interest. So I'll give a very broad talk, and the purpose is to be interesting. And it's up to you to decide if it is interesting or not. So the basic purpose of the talk is to be broad, not to be very detailed, okay? But if you have questions about anything, I can answer the questions or try to answer the questions later. Now, our galaxy consists of about 100 billion stars distributed in a kind of a large disk that has a shape a bit like two fried eggs placed back to back. So it's got a yellow round bit in the middle and a flat disk. And the disk is full of stars, but it's also full of very low density gas called the interstellar medium. And very low density means maybe 1 atom per cubic centimeter, whereas the air in this room has roughly 10 to the 21 atoms, molecules per cubic centimeter. So it's very, very low density, almost a vacuum. But it turns out that you can make that interstellar gas collapse if you squeeze it. So this was realized 100 years ago by a person called James Jeans, some old English guy, who considered the following thought experiment. If you take a balloon and squeeze the balloon, it will get smaller, and the gas inside will get denser. Then when you let go, it will spring back to the original size. And if you do that for a bigger balloon, same thing happens. Bigger balloon, same thing happens. Big as the Earth, same thing happens. Big as the solar system, something happens. But if you go really, really big, when you squeeze the gas in the interstellar medium, it suddenly will spontaneously collapse down into a point. So that's called the Jeans collapse criterion. And it occurs because if you squeeze the interstellar medium enough, eventually its own gravity will take over, and its gravity will exceed the thermal pressure in the gas that's trying to prevent the collapse from occurring. So this has been known for 100 years. We see evidence for it in the sky, and people have many, many computer models to show this. So I have one model here, a very faint laser beam, showing a model of a cloud of gas 500 times the mass of the sun. Temperature is very low, typical of the interstellar medium, 10 Kelvin, and the scale of this thing is roughly 100,000 AU. AU is the distance between the Earth and the sun, so it's 100,000 times the distance between the Earth and the sun. So what's going to happen is this cloud will simply be released, and then gravity will take over. So gravity will cause this cloud to begin to shrink. It's pulling it down into smaller and smaller sizes, and it makes the gas denser, in this case in a very non-uniform, filamentary way. So these yellow regions are higher density and higher temperature. And the model follows them as they collapse under their own gravity. What you notice is, after a while, these small white dots begin to appear. Those small white dots are stars. So this is a very massive cloud, many, many solar masses of material, and it produces many, many stars all at one time. So this collapse is actually quite rapid. The collapse just depends on the density of the gas. G is the gravity constant, rho is the density. It's less than 1 million years for this cloud to collapse, so it's very fast in terms of the astronomical timescale. And the result is a very, very spectacular cloud of stars. So we're pretty sure our sun was born in a cloud like this, and originally had many brothers and sisters, if you like, and they have all now dissipated. They've all now spread away. Now, people who make models like to do fancy things. They like to swing the model around and show you things, but you get the idea. It's gravity that controls the collapse of this cloud. So Jean's mass is much bigger than the mass of the sun. When we go in closer and look at the product of this collapse, what we see is typically material is in a disk, and it's in a disk because of conservation of angular momentum. So the cloud is initially rotating, but very, very, very slowly. As it shrinks, it's like a skater pulling their arms in closer to their body. The rotation goes up faster and faster. And eventually the rotation goes so fast that this collapsing cloud is compressed into a disk surrounding the star. So the sun is in the middle. I can't see my own laser pointer, but the sun is here in the middle, and then this disk is all of the material that collapsed in to make the star, and a bit left over. That's where planet formation occurs. So we're interested in planet formation, we're interested in the solar system, and so we're interested in disks. So that's a picture, that's a painting of a disk. That's not data, it's an artist made that picture. But we do have observations that show this process directly. Here's another simulation. Maybe the lights are a little bit bright for this one. This is inside the collapsing cloud. Here are new stars that are turning on. They begin to emit light because they get hot, and they burn hydrogen into helium. And what you will see from this murky, cloudy, foggy beginning is the emergence of a star and a planetary system surrounding that star. So it goes on for a while. But again, this all happens in 1 million years. So here is the star. This jet is a way that the star tries to lose angular momentum. Otherwise, it would be spinning too fast. And this is a big disk surrounding the star in which planets form. Bang. So the star turns on, and here's the disk, and then there are big planet bodies in the disk. So we understand, or think we understand, this process quite well, because we can see it happening in real objects in the sky. And let me see, I have different pictures here. Here we go, that's good. This is a real picture. This is an image of a real disk of a star. Here's the disk of material. And these gaps, these dark regions, are places where planets form in the disk. So our solar system looked like that in the beginning. So that's all pretty nice. Now, if we look at the solar system sideways, so here's the sun, here's the Earth, here's Jupiter and Saturn is at 10 AU, 100 AU is really far out, 1,000, goes all the way out to 100,000 AU. What we find is that the comets formed here. So comets formed roughly between Jupiter and Neptune. Comets are small, icy bodies, typically kilometers across, not very big. They formed in the vicinity of the giant planets, and then they were kicked out by the giant planets, by the gravity of giant planets, into various places. So one way is they were scattered by a giant planet and then deposited out in this region. This is the Kuiper Belt. So Kuiper Belt is a disk of material from the earliest days of the solar system, and that material grew in the space between Jupiter and Neptune. So we can talk just very briefly about Kuiper Belt. So it's the region beyond Neptune. There's basically no big object there, but lots and lots of small objects. Temperatures there are very low. They're close to absolute zero. So chemistry basically doesn't happen. We think primordial ices are preserved in the Kuiper Belt, and it is the place from which short-period comets fall into the inner solar system. So the source of short-period comets, those with an orbit period less than 200 years, is this region beyond Neptune. And it's a really cool thing because we can see it, and we can measure it, and we can use those measurements to understand both the formation and the evolution of the solar system. So here's just a quick plot to show you the temperature. Kuiper Belt is out here beyond Neptune, and so beyond Neptune the temperature drops. It's below 50 Kelvin. Temperature in this room is 300 Kelvin, so it's very, very cold out there, and basically chemistry does not occur. Now, there are not many complicated diagrams or frightening diagrams in this talk. This is the only one that's really a little bit frightening when you see it for the first time. So here's the distance from the sun. So the sun is here. Here's 20 times the Earth-Sun distance, 60 times, 100 times. So that's distance from the sun. And this is the shape of the orbit. And 0 means a circle, so the eccentricity is 0 means a circle. And up there at 1 is a parabola. It's like a very elongated shape. So objects down here move in circular orbits around the sun. These are the giant planets, Jupiter, Saturn, Uranus, and Neptune. And those dots are some of the Kuiper Belt objects. So we have about 3,000 objects in the Kuiper Belt that have been detected since 1992. Okay. So the aim of modern solar system dynamics basically is to understand this diagram, is why are the objects distributed like this? Why is there a big gap? Why is there this arc? Why are some of these objects in vertical bands? What are these things over here? So these are all current topics of modern planetary science. People always ask about Pluto. Is Pluto a planet or not? And so my answer to that is, tell me which one is Pluto. Do you know? Somebody must know. Which one is Pluto? No? You look like you know, but you don't. So Pluto, Pluto is this one, right there. So there's nothing special about Pluto. It's just one of the dots in this diagram. So that's why we like to think of Pluto as just a Kuiper Belt object, not so much as a planet. Now, how did this structure occur in the solar system? We don't know, but we have models. And one idea, probably the best idea, is that the planets, Jupiter, Saturn, Uranus, and Neptune, were able to scatter bodies from this region, dump them into this region, but then also scatter them out there. So here's a movie, same kind of diagram, distance from the sun and the shape of the orbit. And this is an integration from a computer done in about 2005 that shows the effect of the gravity of the planets on the orbits of Kuiper Belt bodies. And you can see it's very dynamic. It's jumping around. Even the planets are jumping around. They're jumping because the planets scatter a body. When they scatter a body, there's a recoil motion. If you throw a heavy object this way, your body goes this way. So the planets are jostling for that reason. They're also moving radially relative to the sun. The sizes of their orbits are changing a little bit. So this big arc is due to scattering by the outermost planet. These objects are stable because they're far away from the outermost planet. We're up to 700 million years elapsed time now. It looks very stable, but it's actually not stable because if you wait just long enough, it will do this, it will explode. And it exploded because this planet, which originally was over here, was thrown into the Kuiper Belt. So this is Neptune. And the gravity of Neptune is very strong. Gravity of Neptune can basically kick everything around in the Kuiper Belt. So it blew out these objects. That's the idea. So you get the idea the solar system is a dynamic place. Lots of things are happening as a function of time. Whereas before we had Kuiper Belt, everybody thought solar system is like a clock. The hands go around, you know, it's the same again, it's the same again, it's boring. But now we know that that's not the case, that the solar system dynamical history can be very complicated. Now, we still don't really understand the details. When you look closely, the Kuiper Belt is very, very messy. And so people are still interested in understanding that structure. So we go back to this diagram showing the layout of the solar system. Again, the comets formed there. Some comets were ejected to the Kuiper Belt, but others were ejected much, much further out to a second place called the Oort cloud. And this is really large. This is a logarithmic scale. So it's 100, 1,000, 10,000, 100,000 astronomical units. So the nearest star, actually, is here. So objects are ejected from the solar system out to the distances of the nearest stars. And the Oort cloud is this large spherical structure surrounding the solar system for which we have no pictures. It's so big and it's so faint, so far away, we have no pictures. But we infer that it's a spherical structure surrounding the sun containing about 1 trillion comets, 10 to the 12 comets, a lot of comets. And it's the source of the long period comets. I'm going to skip over that to save time, and I'm going to skip over that to save time. So here's what we've got. This is kind of the new view of the solar system. In the Kuiper Belt, we have 10 to the 10 comets bigger than a kilometer, so roughly bigger than the campus of this university. They have orbits that go from Neptune's orbit at 30 to maybe 10,000 AU. The Kuiper Belt supplies the short period comets to the inner solar system. The total mass now is only 1/10 of an Earth mass. It's much, much bigger than the mass of the moon, but it's like the mass of Mars. But in the beginning, we think the mass was probably 10 times the Earth mass. And that mass was scattered away by an instability some earlier time in the solar system. And then for Oort cloud, we have 10 to the 12 comets, a lot of comets, with a total mass that's quite uncertain, but it's probably between 1 and 10 Earth masses. And they're out there at thousands to hundreds of thousands of astronomical units. Now, how do you get something into the Oort cloud? Turns out it's quite difficult. You have to scatter it from a planet, but if you eject something too slowly, it will fall back into the solar system. So here's my demonstration. I eject this too slowly from the solar system. It simply falls back into the solar system. Not good. If the Oort cloud is that ceiling up there, I would like to be able to just throw this and just touch the ceiling. But it turns out to be very, very difficult to launch directly to the Oort cloud. So I'll try again. Not quite. Hopefully this doesn't burst. So I either get it too slow, or I get it too fast. And it's very, very difficult to get it the right speed. Too slow, it falls back. Too fast, it escapes from the solar system, never to be seen again. So we know that something special happened to capture bodies in the Oort cloud because it's very difficult to do that. And in fact, it's estimated that the efficiency of capture into the Oort cloud is between 1 and 10%. That means if there are 10 to the 12 bodies in the Oort cloud now, somewhere between 10 to the 13 and 10 to the 14 were ejected in the early days of the solar system. And most of them were lost. Most of them just got out. They drifted away into the interstellar medium, back between the stars. We thought never to be seen again. So, here we are with that same diagram again. We have comets forming in the vicinity of the giant planets, being scattered by the gravity of the giant planets. Some of them fall into the region we call Kuiper Belt. Others fall into the region we call Oort cloud with a bit of difficulty. And then others are launched right out of the solar system, and they're never seen again. They're gone. And in fact, most objects are ejected from the solar system in the early days. Now, the deal is that we did not know of these objects, which are called interstellar interlopers, until very recently. And in fact, we only know of 2 right now. We have 2 discovered in the last 7 years. So I need to talk about those 2, just to say something about them. Now, you can say, well, how do you identify them? That actually is fairly straightforward. If you look at their eccentricity, all of the comets in the solar system have eccentricity less than 1. Their orbits are bound gravitationally to the sun, so E is less than 1. That line shows the long-period comets, which are very close to 1 because their orbits are very, very big, but they're still bound to the sun. We have these 2 things. 1I, the names are horrible. 1I Oumuamua and 2I Borisov have eccentricities very, very much bigger than 1, meaning that their orbits are hyperbolic, not elliptical, not even parabolic, but hyperbolic. They're not held by the gravity of the sun. They feel the gravity of the sun, but they just continue on their way. So those are the 2 things that have defined this new subject, and it's a very hot subject in the study of the solar system. The deal is that if the sun lost 10 to the 14 comets to the interstellar medium, and if every other star in the galaxy lost 10 to the 14 comets to the interstellar medium, there are 10 to the 11 stars, 10 to the 14 comets per star. That's 10 to the 25 comets drifting between the stars. 10 to the 25. That's a big, big, big number. But space is also very big. So even though you have 10 to the 25 things in the galaxy drifting around, we were not able to accurately estimate how frequently they should fly through the solar system. So we didn't know how long we'd have to wait until we saw one coming back into the solar system. Estimates range from 10 years to 1,000 years, something like that. But again, luckily we've got 2 in the last few years. So the easy one to talk about is Borisov, because Borisov looks like what we would expect. So that's a picture of Borisov that I took with a space telescope, and it looks like a comet. It's a small, solid body that, in the heat of the sun, is sublimating and blowing out ices that drag out dust particles from the nucleus. Its eccentricity is above 3. Its minimum distance from the sun is about 2, so beyond the orbit of Mars, and the inclination is 44 degrees, so not too far from the plane of the solar system. So if you look at that here, you can see that the dust is very obvious. These are stars and galaxies in the background, but that's the body. It's blowing out dust because of the heat from the sun, and then the dust is pushed away from the sun by radiation pressure. So it's just like a comet in the solar system. So no big deal there. And we have models of that, Monte Carlo models of the motion of the dust. Everything's very pretty. We have measurements of the composition. Composition is kind of like the composition of ordinary comets from the Kuiper belt and from the Oort cloud. So basically, no big surprises with Borisov. Even this is not a surprise. These are pictures, again, from Space Telescope. And you see that the nucleus is single, except here, it's not. It's like a peanut. It's double. And we see that in comets as well. Sometimes the nucleus will split off a piece, and that piece will drift away. So really, Borisov, very, very much like comets in the solar system, sort of what people would expect. However, that's not true for the other one, for Oumuamua. So Oumuamua was discovered making this, let me just try that again. All right. Discovered making this journey through the solar system. It came in with an inclination of 120 degrees. It means the planets go around this way. Oumuamua was coming in the opposite direction. It came to a very small distance from the sun, 0.26 AU, and eccentricity is bigger than 1. It's definitely not bound to the solar system. So these are the orbits of the planets. Here's the motion of Oumuamua passing through the planetary region. There's the Earth, the third planet, goes way inside that, through the plane, and then back out the other side. The whole thing came and went in a few months. So we only had a few months to study this. It took only 10 years to cross from this side of the orbit of Neptune to that side of the orbit of Neptune. Now, what did it look like? Here's the problem. It looked like that. See that little dot? That's it. Pathetic. Not like a comet. And so immediately that's a bit strange. Why is it like an asteroid, not a comet? Where's the ice in this body? Got really hot near the sun. Where's the ice? Didn't sublimate. That's very strange. So it does not look like Borisov, shown at the bottom. So they look very, very different from each other for reasons which are not yet very well understood. In addition, Oumuamua has a very, very large light curve. So a light curve is basically a measure of the shape of the body. So you can probably see this controller. When you see the controller side on, it has a big cross-section and it is bright. When you see it end on, it's a small cross-section and it's faint. So as it rotates, it goes bright, faint, like that, up and down, like a sine curve. And so that's sort of what you see in the brightness plot shown here. It is a body that is very, very elongated. So first estimates were it's like this, a very ugly object. It looks about 6 times as long as it is wide. But in fact, we have reason to think that it's probably like this. It's more like a hamburger, like a giant hamburger, 100 meters across from here to here, and rotating in some axis like that. So it goes up and down because you see a big side and a small side, a big side and a small side. And the rotation period is about 8 hours, something like that. So I skip over these just to save time. Now, the other very, very strange thing about Oumuamua is that it shows non-gravitational acceleration, right? So there's gravity, we have Kepler's laws. Those laws work really well for bodies in the solar system. But for some bodies, some comets in particular, you need another force. So that extra force is called a non-gravitational force. And in comets, the non-gravitational force is due to the asymmetric release of mass. So the day side of a comet nucleus is hot. Most of the mass is sublimated from the day side, goes off towards the sun, and that exerts a recoil away from the sun. So again, if I throw a mass in this direction, I'm going to recoil back away from that. That is responsible for the non-gravitational acceleration of comets. And non-gravitational acceleration of Oumuamua is very strong. It's detected very clearly. So that's weird, because it doesn't look like a comet. We don't see any evidence for mass loss, and yet it shows recoil, which normally we would associate with mass loss. So that's a big fuss. People are up in arms about that. People don't know how to interpret that. But there are two basic ideas. One is that it is mass loss, but for some reason we can't see the material that's being lost. So this is just the force law, the speed of the ejected material, the rate of loss of mass, the density of the nucleus, the radius of the nucleus, and that's the acceleration. So we can measure this, we know something about this, and we can see what mass loss would be needed to cause the non-gravitational acceleration of this body. So those are the variables. I'll just skip over that. Turns out you don't need much. You only need a kilogram per second, which is, you know, even I could eject that much material if I had to. Not for very long, perhaps. But the trouble is we don't see that. Now, why not? Well, we need that material, but maybe it's in a form that we cannot easily see. So people have published different models, different ideas. One is that Oumuamua is the coldest object ever detected, formed in a place where molecular hydrogen, which is the dominant molecule in the universe, molecular hydrogen froze solid, and then that molecular hydrogen is responsible for the recoil, the non-gravitational acceleration. That's a wonderful idea, except that it's basically impossible to keep a molecular hydrogen iceberg stable for any amount of time, because it would just, any temperature bigger than 6 Kelvin, it would sublimate away. So this idea probably is a little bit ridiculous, not good. Another idea is molecular nitrogen. Like the atmosphere in this room, molecular nitrogen also is very volatile, and it is very hard to detect spectroscopically using astronomical techniques. So maybe Oumuamua is ejecting nitrogen. And these ideas just get, you know, crazier and crazier. Many problems with that. One problem is there are not many places where you find big puddles of nitrogen. You know, Pluto is one. Pluto has a nitrogen body on its surface. It's a lake, but that's it. There's not much nitrogen lying around in the form of ice. And so it's hard to see how you would get enough nitrogen to power Oumuamua. Carbon monoxide is a good one because carbon monoxide is abundant in comets. The trouble is that we have an observational limit to the amount of carbon monoxide in Oumuamua, and it's very, very small. It's 100 times or 1,000 times less than you would need to create the non-gravitational acceleration. So it's not CO. And then there's another idea that it's hydrogen but released from material that's been chemically processed by cosmic rays. And that's a possible idea, but it has many unknown parameters. So I don't know how much we can trust that one. So the bottom line is we don't know why Oumuamua has this non-gravitational acceleration. The other idea is, well, maybe it's not mass loss at all. Maybe it's due to radiation pressure. So you know that photons have momentum, right? Individual photons have momentum, but it's very, very small. On the other hand, if you have a lot of photons, or if you wait a long time, the effects of radiation pressure might be detectable on Oumuamua. So the second kind of set of ideas is that Oumuamua is being pushed by the radiation pressure of sunlight. Okay, and if that's the case, we can estimate from these quantities, we can estimate what must be the density of Oumuamua. So it turns out that you would need it to have a very low mass per unit area. And in fact, you could do that if Oumuamua were very, very, very thin, like a sheet of paper. So if the density is the density of paper, it's roughly this, and the thickness is about 1 millimeter, so it's 10 sheets of paper, then maybe you can explain Oumuamua. The trouble is, it's kind of weird. It's strange to think that Oumuamua could be a sheet, not a ball, not a round thing. Alternatively, it could have a round shape, but it could have a round shape and an extremely low density, 0.01 kilograms per cubic meter. Remember, the density of air is 1, so it's 100 times smaller than the density of air. And that's kind of crazy too. So let's talk about that, about low-density materials. So there is this stuff called aerogel, which people make for use on space shuttle or spacecraft and other purposes. It's very low density, but it's not that low. Typical density is about 1/10 of the density of water, so 100 kilograms per cubic meter. The very lowest density material ever made is 0.2 kilograms per cubic meter. And it's basically a set of fibers, silicon fibers, with a lot of vacuum between the fibers. So maybe Oumuamua is like that, but that's a bit worrying too, because we have no other examples of bodies in the universe that are like that. So again, where we don't have much certainty, we have many suggestions, we have many models. So people are making models of fractal growth. So you can think of Oumuamua as being like a ball of straw or hair or something, very low density assemblage of particles. And it grows in that disk around the central star. As it grows in radius, it's a fractal, so it becomes less and less dense, reaches a minimum in this model, which is about right. It's less than the density of aerogel by a large margin. And then when it gets bigger, it self-compresses under its own gravity, and so the density goes up again. So again, it's a model, but in astronomy there are many, many models for every good observation. That's kind of a problem. And many of the models are crazy, and it's hard to tell which ones are crazy until you get better data. So at the present time, we cannot rule out some kind of a fractal, very, very low density constitution for the nucleus of Oumuamua, although personally I think that's a little hard to believe. So again, density of water is up there, density of air is down there, and the density of Oumuamua is that green dot down at the bottom. It's crazy. It's crazy low density. Okay. Skip over that to save time. So we have basically fractal models. So maybe Oumuamua is made of this very low density porous aggregate. We don't really know how they could form. And we don't really know if they could survive in the interstellar medium, but maybe they could. Or Oumuamua is being pushed around by radiation pressure. So this is a sheet of plastic mylar, which reflects photons very well. It's very thin, not very dense, and it has a mass surface density that's about right, 1/10 of a kilogram per square meter. The trouble is, you know, does nature do that? Does nature make sheets in space? Doesn't seem right somehow. Okay. Lastly, let me talk about the population. So, how many of these things are there? This is the most incredible thing. This is the brightness these curves here show the brightness of Oumuamua as a function of time in 2017. So here's January the 1st, and here's December the 31st. So that's the year. The brightness was very, very low because the object was far away from the Earth. And the brightness then shot up, reached a peak up there at about 20. Don't worry about what 20 means. And it was discovered right there. That D is when it was discovered. So it was discovered only because its brightness just popped up enough to be detected, and the rest of the year it was not detectable. So that alone tells you that there must be a lot of other bodies like Oumuamua, because what's the chance that we will be able to detect it at the exact moment it became bright enough to detect? The answer is very small chance. And you can work out the probability for this detection, and it doesn't make any sense to have found Oumuamua unless the density of objects is quite high. So the number of bodies that we have, like Oumuamua, is about 1 every 10 cubic astronomical units, which means there are 10 to the 15 in a parsec, a cubic parsec, which is the distance between the sun and the nearest stars. The solar system contains roughly 10,000 Oumuamuas closer to the sun than Neptune right now, at any time. Just based on this detection of Oumuamua, there must be a huge number of bodies in the solar system, but they're almost all too faint to be seen. And so the reason that we saw the first one is that our technology is getting better, telescopes are getting better, we can see fainter, we can look at more of the sky, but we're just seeing the tip, literally the tip of the iceberg. So there's a huge number of these bodies flying through the solar system. Again, it takes about 10 years to cross from one side of the solar system to the other. That means that these interstellar bodies enter the solar system about 1,000 times per year. So that's 3 every day. So while you sleep, another interstellar body comes into the solar system. And then on the other side, a body leaves the solar system in steady state. If you work it out, that density implies between 10 to the 25, 10 to the 26 Oumuamua-like bodies in the plane of the galaxy, which is roughly consistent with the idea that all stars are ejecting comets in the way that the sun did. Very hard to estimate the mass because we don't have good estimates of the sizes or densities of these things, but you know, some big fraction of an Earth mass of bodies contained in these interstellar objects. So the kinds of questions we have are things like, why does it have that shape? It's so elongated. No asteroids are like that. No comets are like that. Why does it have that weird shape? We don't really know. Why does it show non-gravitational motion but has no appearance of a comet? It doesn't seem to be ejecting any mass. Where did it come from? We don't know. Where's it going? We don't know. And how long has it been out there? We don't have any good ideas for that either. So because this is a new field, the questions outnumber the things that we know by a factor of 100 or something. We just don't know what's going on. But that's what makes it exciting. So these are numbers that we have and can trust for the 2 interstellar bodies. So it's not like we're completely ignorant, but we need many more numbers to understand these objects better. Now, it's kind of interesting to look at what happens to a body. If you release a body in the plane of the galaxy, it gets scattered and its motion is basically being kicked around. It's like putting a football onto a football field and then having everybody kick the ball. The ball just goes around, and the more you kick it, the faster it goes. So if you release an object into the galaxy, its speed increases with the amount of time that it's been out there, scattered by stars. So we have, this relation is a blue line based on measurements of stars. We have for 1i and 2i, these 2 estimates of speed that give 2 estimates of the age. So we think Oumuamua probably has been out there for 100 million years, maybe 200, maybe 300, and Borisov has been out there for maybe 1 billion years. And we think it's probably, in both cases, a body ejected from the disk around a young star somewhere else in the galaxy. We'll never know which star. We'll never know exactly when. And it was kicked out by the gravity of some planet in the disk around that star. So the residence times are long. It's hundreds of millions or billions of years for these things. All right. Let's just do this one. It turns out that when you have a planetary system in a disk, not only small bodies can be ejected, but planets can be ejected as well. So we know in the interstellar medium, we see planets which are not associated with any star. The free-floating planets have been kicked out of their own planetary systems. And it's just kind of for fun, if you plot those planets, this is the density of planets, you plot those planets on the same plot as Oumuamua, you have a size distribution index of about -3. So if you increase the size by a factor of 10, the number of bodies decreases by a factor of 10 to the 3. And that is an interesting observation because it means that if we look for free-floating planets and we get a little bit better at finding free-floating planets, we should find many, 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 many objects in here between the big guys, that's like a Jupiter, and the small guys, that's Oumuamua. So this is kind of a new discovery space that will probably open up in the next 10 years, or something like that. So, now what is Oumuamua a spacecraft? You've probably heard this idea that Oumuamua could be an alien spacecraft, right? That idea comes from the strange motion of Oumuamua, from this non-gravitational acceleration. And from that model, which suggests that it could actually be a sheet, like 10 stacks of paper, very, very thin body. You know, nature probably doesn't make thin sheets in space, but we could. We make sheets of plastic all the time for all sorts of purposes, and we even put some into space. So some people have speculated that Oumuamua is a light sail. So there's this, this guy, Avi Loeb, in Harvard, who's made a big deal about saying that Oumuamua is an alien spaceship. So that's fun, but it's kind of ridiculous. He's actually got books in different languages. There's a book in German. He's got artistic pictures of spacecraft saying that that's like Oumuamua. He has pictures of himself staring off wistfully into space, looking for aliens. He has a lot of things going on. It's very good for publicity, but I think it's kind of ridiculous because, you know, what alien civilization is going to launch 10 to the 26 spacecraft, 100 meters in size or more? Why would they do that? Doesn't make any sense. And if they did launch a spacecraft to check us out, why would it miss the Earth by 0.2 AU? That's a big, big distance. That's 30 million kilometers. Why would they miss? So maybe the aliens are incompetent. Maybe they don't know what they're doing. But still, why would they launch so much junk into space? It's hard to imagine. What would be their purpose? So there's no evidence that Oumuamua is a spaceship. But of course, in science, you know, it's always very, very difficult or impossible to say an absolute no. So keep our minds open to that remote possibility. Okay, so we have many, many questions that need to be answered about that. I either could stop now and have some questions, or I can have a little bit more discussion about aliens. What do you think? You want some aliens? Okay, let's have some aliens. So the alien idea is not completely stupid, right? Because the Earth is 4.5 billion years old, but the universe is 13.5 billion years old. So there are more than 8 billion years, 9 billion years of time before the sun even existed. So before our planetary system even existed, you know, other stars existed and other planetary systems existed. And we know that the number of planets is greater than the number of stars. So planets have typically, stars have typically more than one planet each. There's lots of planets. And that means there are lots of places for extraterrestrial life to have developed. And so there's all sorts of speculation about that. What would life be like if it had been there, you know, 1 billion years before us? What would happen in that huge amount of time? It's incomprehensible. So I just thought it'd be fun to list a few examples of problems that we face in the search for extraterrestrial intelligent life. So bacteria, looking for bacteria on Mars or some satellite, that's one thing. But looking for intelligent life, to me, seems to come down to several problems. I call this one the ant problem. This is the HAL problem. This is the gray goo problem. There's the self-destruction problem. And there's the contact problem. So I'll just talk about these things very briefly, and then I'll stop. And it's just for fun, because this talk is meant to be fun in some way. So the ant problem is this. If you sit on the grass in the summertime, and you're eating a sandwich or a bowl of noodles or something, and an ant crawls up your shirt and crawls over your face, you know what it is, but the ant doesn't know what you are. So the ant does not know that it's walking on the surface of a vastly more intelligent human being. It feels your skin, maybe it notices the hairs, it doesn't know what they are, it feels the temperature perhaps, but it has no idea that it's standing on the surface of an entity that's orders of magnitude more intelligent than it. It just cannot comprehend this more advanced life with its tiny, tiny brain. So that's obvious in this picture. Here's an ant that's picked up a microchip in its mandibles. You know, the ant doesn't know what that is. Has no idea that that's really alien technology for it. It cannot recognize it. So the ant problem is that this must be true for us as well. So we will not be able to recognize life much more advanced than we are. Now, we don't know, you know, how far we can detect, we can recognize life. So think about it, you know, if you tried to make a phone call to Galileo, Galileo would have no idea what's going on. Galileo didn't know about electromagnetic radiation, didn't have electronics, didn't have the concept of communication, you know, at a distance through a device, nothing. And that's only 400 years ago. So he basically would have regarded us as gods, in essence, or aliens. So maybe this window of visibility is very small. It may be that we can only recognize life more advanced than we are in the next 1,000 years, or something like that, maybe 10,000, but it's not 1 billion years. Life evolving for 1 billion years is almost certainly incomprehensible to us. So if we're searching for advanced life, we're going to have a real problem identifying it if it's very advanced. The HAL problem is related to computer progress, computer intelligence. So there's this very famous Moore's law, which said that the speed of a computer doubles every couple of years, right? The number of microchips that you can put on a wafer doubles every 2 years. And so what that means is the phone in your pocket now, in 2024, is more than 1 million times faster than the most powerful computer in the Apollo spacecraft in 1968. So computing power just goes up, but biology doesn't increase that fast. And so the thought is that, as you know, computers may become sentient. They may develop essentially personalities and independence. They may think for themselves. And when that happens, they may or may not be friendly to us. They may not actually care about our development. And so when you think about advanced life, you have to wonder, is there a barrier caused by what I call the HAL problem? This is HAL from 2001, the best movie ever made. So the idea there is that, you know, our evolution may be coming to an end. Biological evolution may be almost over, and we're going to go into this different kind of evolution. Maybe we'll merge with silicon life, or maybe it will just wipe us out. And when we're searching for intelligent aliens, you know, maybe we should be looking for some kind of electronic life elsewhere. The gray goo problem is that advanced technological civilizations like ours might invent some very simple technology for a good purpose and then lose control of it in an unforeseen way. So for example, we know that plants are very efficient in converting sunlight into energy through chlorophyll. And people are trying to replicate plant technology and to do better than plants. The efficiency could in principle be higher. What if we made an artificial plant that was more efficient than real plants, and that plant escaped into the environment? It would outcompete with real plants. The problem with that is we need real plants because we eat them. That's the base of our food chain. So if we wipe out the real plants and replace them with man-made plants, that's bad for us. Likewise, conceivably, we can invent a copper-eating nanobot, so something that would basically recycle your phone. It would go in and take the heavy metals out of your phone. What if that got out and escaped into the environment and ate all of electronics everywhere? So every device that we know and love would be gone. That would be fatal as well. So there are many examples like that. The point is that we can invent a simple technology for a good purpose, but then lose control of it. It's a bit different from AI, where we're trying to invent a very advanced technology, and then we lose control of it. We're just trying to do something simple, but we can lose control of that too. There is the self-destruction problem. Many people think this is the biggest obstacle to the discovery of advanced life and to the existence of advanced life. The trouble is that technology makes killing easy, okay? So we have very powerful weapons, and we always use them. And I do have a video which does have sound, and I'll show this. So here is a bunch of monkeys. Just watch this movie. So that's one monkey against 20 monkeys. They do have weapons, right? They've got claws and they have teeth. They can bite. But the objective here was not to kill. So nobody was killed in this confrontation. One group won. The 20 monkeys won. They pushed the other guy up a tree. But the objective was not the extermination of the single monkey. But by comparison, by developing weapons, we've gone essentially in just a few thousand years. We've gone from this to this, where you don't even know who you're killing, right? So you have a confrontation with somebody, you release some nuclear bombs, everybody dies. So the self-destruction problem is that we might do that, and advanced civilizations might all do that inevitably, because this development of weapons is part of our tribal identity, it's part of our evolutionary identity to fight to preserve ourselves and our group against opposing groups. So maybe that is an unstoppable impulse that will necessarily lead to our destruction and has already led to the destruction of many advanced technological civilizations. So self-destruction problem, you know, some people say we're within 100 years of this self-destruction of our society. Maybe that is just general. Maybe that always happens. If that's the case, it'll be very hard to find advanced life because there isn't much out there. It keeps knocking itself down. And then the contact problem. You know, on our planet, we have contact with other species, and that contact is often not good. So we often find other species and we eat them. And so that's not good for the other species. They don't like that. Perhaps the same could happen in contact with alien species. Even when we contact other members of our own species, sometimes the outcome is not good. So we have examples of slavery, for example, and war, and then the spreading of disease between different human populations, all basically in the same group, but still killing each other in all sorts of different ways. And so we have to wonder if that has happened elsewhere in the galaxy, and that if contact with advanced alien life would necessarily be good for us. And it may be that the number of advanced civilizations is reduced by contact, so that the impulse is to communicate, but somehow also the impulse leads to the destruction of many of these alien societies. So I thought it would just be fun to mention those possibilities in the context of Oumuamua, which is not an alien spacecraft. It's not, but it could have been. Could have been. You cannot rule out that possibility. Okay, so first of all, interstellar interlopers like Oumuamua are not evidence of aliens. For finding intelligent life, we have to accept the ant problem is real. Our brains just cannot conceive of life very different from what we are now. We have this problem of travel. It just takes a long time. We're confined to much, much less than the speed of light. It takes forever to go anywhere, so it's going to be very difficult for us to go out and find life. We can only recognize life that's not too far away in distance and not too far away in evolutionary state because of the ant problem. And all of these things conspire probably to provide an answer to the Fermi paradox, which is if aliens are common, why don't we see them? So the summary is really this. The future of astronomy is widely recognized to be biology, that the major driving force in astronomy is the search for life elsewhere. Not just intelligent life, but also simple life, like bacteria that we might find in the solar system. Similarly, the future of biology is astronomy, because we think of biology as just this Earth-based thing, but actually, you should think of it as a cosmic phenomenon. It's going to be present on all sorts of planets, all through the universe, if only we could find it. And the search for this extraterrestrial life is the defining objective of our time. I think it's like the most exciting, highest level thing that human beings can do. So anyway, that's about time for me to finish. Most of the talk is about interlopers. It's real, the interlopers are real. It's a background on the solar system, Kuiper Belt, Oort cloud, ejected objects. Last part is a bit crazy, but it only sounds crazy because we don't have any data to pin down the number of advanced life forms out there. Okay, thank you.
Thank you for your magnificent speech on visitors from beyond the solar system.
谢谢大卫·朱维特教授的精彩分享，让我们获得了许多太空科学领域的宝贵知识。
We will now proceed to the Q&A session. Dear teachers and students, if you have any questions, please raise your hands and our staff will pass you the microphone.
现在进入问答环节，有疑问的老师或者同学们可以举手示意，欢迎各位踊跃提问。有同学有问题吗？有请那位白衣服的女同学。
Hello, Professor JEWITT. Thank you for the great talk. So My question is, those interstellar bodies have really high velocities, and also they're not always directly detectable. So what if they hit Earth someday, and what can we do to better detect them so that we can predict their trajectory, and if they're going to hit Earth, we can protect ourselves?
Okay, so the good news is, yeah, they travel really fast, so they have a lot of kinetic energy per unit mass. So if we did get hit, it would be not good. But the number of interstellar bodies, although it's huge, is still very small compared to the number of asteroids that hit the Earth. So work that out, and the ratio is 10,000 to 1. So we get hit by 10,000 asteroids from, between Mars and Jupiter. 10,000 asteroids, bigger than a kilometer, for every one interstellar object bigger than a kilometer. So don't worry about that. Asteroids, you can worry about asteroids. So we get hit by a kilometer-sized asteroid roughly once every million years. It's quite frequent. And a kilometer-sized asteroid would cause damage over an area, destruction over an area like a European country, for example. We get hit by a 10-kilometer asteroid every 100 million years, which is still short compared to the age of the Earth, and that causes global destruction, causes mass extinction, right? So we have this mass extinction, the KT extinction, from 65 million years ago, caused by a 10-kilometer asteroid that hit in what is now the Gulf of Mexico. So it does happen. The timescale is not negligible, but it's not likely to happen in your lifetime, and even less likely to happen in my lifetime. Yeah.
Okay. Thank you.
Sure.
好，谢谢这位同学。Thank you, Professor David Jewitt. 还有同学要提问吗？ Is there any questions?
Are there any aliens in the audience?
Sorry.
Show your hand.
Oh, here. Hi,
Alien,
Professor.
alien.
Just a follow-up question. The high-speed body comes, the interstellar.
Yeah.
So can we capture them to study biology?
No. Can we capture them? No. But people are talking about ways to send a spacecraft to an interstellar body. So the special thing is, everything else in the solar system, we think, was formed in the solar system. All the comets and the asteroids were formed in association with the sun. And they've been going around the sun forever. The interstellar interlopers are the only bodies which didn't form around the sun. They formed around some other star, probably really far away, probably a really long time ago. So the thought is, if you could sample the material from an interstellar interloper, you would be able to sample the material from the planet-forming disk around another star. And there's no other way to do that. So it'll be interesting because, is the composition going to be the same? Are these bodies going to have the same rocky iron composition as the terrestrial planets on the Earth? Do they have craters on them, like the craters that we see on asteroids? All sorts of questions that could be answered. But the problem is, it's really difficult to catch up with even with an object orbiting the sun. It's very difficult to accelerate a spacecraft to catch up. And if it's moving very fast, and the interstellar objects are all moving faster than the escape speed from the solar system, then we don't yet have a way to do that. So if you can't catch up, maybe you could hit it. Maybe you could shoot it with a spacecraft. And so people are thinking about that too. That's not so good because it destroys the spacecraft.
谢谢这位同学。Thank you, Professor David Jewitt.
Yeah.
Is there any questions more? 好，我们公关同学把麦克风递到前面的这位老师这里。对 ，Welcome.
Very interesting, but in terms of advanced civilizations and why you might not see them, if you look through the Earth's history, obviously there are many mass extinctions where the dominant species just fades away and is replaced by something else. So it may be more reasonable to think that you don't get a billion years of evolution on a species for it to become so advanced that it can be like us being the ant.
Yeah.
So
I
anything to say about that?
No, I agree with that, and that's basically what is meant by this self-destruction problem. Like, we will extinguish ourselves. We provide our own giant impact, essentially, by detonating too many bombs, releasing a bioweapon, or doing something bad. So yeah, you could truncate that. The question then is, if we did that, if we destroyed civilization with some weapon or weapons, how long would it take to come back? It's one question. Because not everybody would die. Even in total nuclear war, not everybody dies. So there would be survivors. How long would they take to rebuild civilization to the same level? And how long would they have to go higher than that? And so you can imagine kind of a step like, we get better and better, we kill ourselves. And then we get better and better, and then we kill ourselves. That's possible as well. Yeah. But the timescale for natural extinctions probably is much longer than the timescale for killing ourselves through our own stupid behavior. That's my guess. Yeah.
好的，我们有请下一个。
Hi, just another question about the Fermi paradox.
Yeah.
Would you like to say some words about the dark forest hypothesis or idea?
No, would you like to?
No. Except that, no.
But I understand your question. There are many suggestions for the resolution of the Fermi paradox. So one that became very popular recently because of a movie is the idea that we're not real, right? The idea is that we are in a simulation. Yeah. We're in a simulation of a more advanced civilization. So we can really know nothing about the universe because everything that we perceive is programmed into us. That's one kind of crazy idea. What's that movie called? Matrix. Right. I think that's nuts, but there are people who buy into that idea. Another idea is that we're in a zoo, that we're in an alien zoo and they're looking at us and, hey, look at those guys. They're all sitting there listening to that idiot giving a talk. Why are they doing that? And they're laughing. They're having a good time laughing at us. Another idea is that they're frightened of us. It's hard to believe, but they're hiding from us because they don't want to be detected. There are many, many suggestions. Yeah. I think the true answer is probably too early to make any strong conclusion based on evidence, about the abundance of advanced life, despite all the stuff I said. So we've only been looking with radio telescopes in a very, very limited way and for a very small amount of time. And there's a few laser-based searches, but they're almost, nothing. A few hours here, a few hours there. So we haven't really done a very good search for intelligent life with any technique, even the ones that we could execute, because in astronomy, astronomers tend to be very conservative, and they're very focused on doing their own narrow thing. And if their narrow thing is not the search for alien life, then it doesn't get money. Nobody wants to do it. It's too crazy. It seems too crazy. But it's only too crazy until you discover alien life, and then it's the coolest thing in the world. Yeah. So I think it's too early to conclude Fermi's paradox is a real paradox. That's my personal view.
好，谢谢。请问还有同学要提问吗 ？Is there any questions?
Hello,
Okay.
Professor
David.
I have one question. I feel very interesting about the radiation pressure. Just now you said. You see the near side of the moon is different from the far side of the moon. I always think the radiation from the Earth should be responsible for the difference. would you please give some
Radiation from the Earth responsible for?
the difference between the near side of the moon and the far side of the moon?
Yeah. So you mean the moon has the Maria on Earth's side? The basaltic lava is on the Earth-facing side, right? It's because the moon is not a spherically symmetric body, so it's been locked into this orientation by tides, by tidal dissipation between the Earth and the moon. The radiation force is really, really, really small. It's really small.
But the near side always facing the Earth, and the time is very long, maybe several billion years.
Yeah, but that's because of tidal dissipation. So we know about that pretty well because, you know, on the moon, the various spacecraft deposited mirrors, and so you can use it. You can send a laser and measure the distance to the moon very accurately, maybe this accurate, and we see the moon drifting away. I think it's 4 centimeters per year, moving away from the Earth because of tides. So we understand the tides pretty well, and we know that the tides are responsible for this drifting of the moon, and they would also naturally explain the tidal locking of the moon. And it's not just the Earth's moon either. Pluto has a big moon called Charon, and its moon is also tidally locked. So one face points at Pluto all the time. And the satellites of Jupiter, Europa, Io, Europa, Ganymede, Callisto, are also tidally locked for the same reason, tides. So tidal force much, much bigger than radiation force.
Thank you.
Yep. 好的，感谢各位的提问。Thank you, Professor David JEWITT, for answering the questions. And now we will let our PR students to send flowers to thank Professor David JEWITT for giving us a wonderful lecture today. Let's welcome.
感谢大卫·朱维特教授的精彩回答。现在有请公关同学为我们致送鲜花。让我们再次掌声感谢大卫·朱维特教授。
Let's give a big round of applause to thank Professor David JEWITT.